Welcome to Riemannian Geometry Lecture 1b. In this lecture, I'm going to give the definition of a Riemannian metric and a Riemannian manifold. And then I'm going to give a way to understand a Riemannian metric locally, which will be very useful for computation. In particular, we'll have a look at some very basic examples. But let's begin by noting that Riemannian geometry, as we understand it, was first invented by Riemann, and so it bears his name, in his Appellation thesis. And he announced his results in his inaugural lecture for his job in 1854. So this must certainly rank as one of the greatest maths job talks ever. Now, the key idea that Riemann had is that you want a way to measure distance on your space, which varies from point to point. In fact, he was one of the first people to think about considering such a thing in dimensions greater than 2 or 3, so in arbitrary dimension. Now, the definition that we're going to give isn't exactly the same as what Riemann did, but is in the same spirit of what he was talking about. And the definition that we can think of informally in the following way: that a Riemannian metric on a manifold is a smooth choice of positive, definite inner product on each tangent space to the manifold. So remember that if you have an n-dimensional manifold, then every tangent space is an n-dimensional vector space. And so we're just talking about a positive, definite inner product on each of those vector spaces. Now, this fake definition is actually good enough for this course, but let's give ourselves the formal definition so that we have it to hand. So the formal definition is if we're given a manifold M, then a Riemannian metric G on M is a section of the second symmetric power of the cotangent bundle of M. So if you don't remember what this is, I recommend that you have a look back at the relevant lecture from the differentiable manifolds course. And it's not just any section of this bundle, it is a positive definite section. What that means is that for every point in the manifold M, we have a positive definite symmetric bilinear map. So it's a map from two copies of the tangent space to M at P, which we denote by T sub Pm, to R. Remember, these are real vector spaces because this is a real object, the manifold. And so this is all that we really need to understand for this course, is that we have this positive definite inner product on every tangent space that varies in a smooth way as we vary P. So this is going to be the fundamental object that we want to study in this course. And then we call the pair Mg, so M is a manifold, G is a Riemannian metric on that manifold, a Riemannian manifold. Now, what you'll have seen in the differentiable manifolds course is that every manifold admits a Riemannian metric. In fact, it will admit infinitely many. And so there are two fundamental questions, which are kind of the opposites of each other, that we want to understand in this course. The first is, how does the choice of manifold, in other words, the smooth manifold, the underlying topological space, restrict the Riemannian metric? And the converse to that is, suppose that I have some certain type of Riemannian metric on my manifold, what does that tell me about the manifold? And these are the central questions that are going to guide us throughout this course. We want to understand the interaction between just the differentiable manifold structure and this Riemannian metric, the choice of Riemannian metrics that we can put on it. Okay, so now I want to understand how we can think about Riemannian metrics locally. So recall that if I have a finite dimensional vector space, V, with a positive definite inner product on it, which I just denote by these angle brackets, then we can always think of this inner product as a symmetric positive definite matrix. But I can only do that if I choose a basis of my vector space. So that's very important. So if I choose a basis of the vector space, then I can identify the inner product with a symmetric positive definite matrix. And of course, we know that if we change the basis, then we'll change this matrix. Okay, so then it's important for us to know what is a natural choice of basis for our vector spaces. So of course, the vector spaces that we have in mind are the tangent spaces to our manifold. So that means we want some tangent vectors, or more generally, we want some vector fields. So let's just recall the following definitions from the differentiable manifolds course. We have the standard vector fields on Euclidean space Rn. We'll denote them by partial I, and they're just the vector fields d by dxi. So they're just the differential operators that differentiate in the xi direction. So we have n of those. They give us a basis for the vector fields. So every vector field on Rn can be written as a combination of these partial i's. Now, given any chart u phi, so let's recall that if we have an n-dimensional manifold M, then we have these charts, which are a pair of an open set U on the manifold and a map phi going from U into Rn. Then we get these coordinate vector fields on U phi. So these are vector fields defined on the open set U on the manifold M, and they're given by taking the push forward of these standard vector fields by the local diffeomorphism phi inverse. So this is a well-defined diffeomorphism on phi of u, which is an open set in Rn. And this will give us a basis for the vector fields on u in M. And these coordinate vector fields will then be very handy for us in describing Riemannian metrics, as I will now explain. Because you see, given any chart u phi on a Riemannian manifold Mg and a point P in this open set U on M, then we have a basis for the tangent space to M at P given by this n tuple of vectors, x1 of P up to xn of P. These are n linear independent tangent vectors, so they give us a basis for this tangent space. And so we have the basis for every point in U. And what that means is that we can evaluate G on this basis and get ourselves a symmetric positive definite matrix. And of course, this will be thought of as a symmetric positive definite matrix of smooth functions, because as P varies over the open set U, we'll then get a family of smooth functions. Okay. So we can see that using the coordinate vector fields, we can think of a Riemannian metric as nothing other than a symmetric positive definite matrix of smooth functions. Now, it's also important to remember that our open set U in M is diffeomorphic to an open set in Euclidean space. And what that will mean, as we shall see, is that it's enough to understand Riemannian metrics just defined on open sets in Euclidean space. So this was one of the take-home messages from the study of manifolds, is that many things can be understood locally. So you can just do all of your calculations on Euclidean space and then patch them together to understand what the answer is on the whole manifold. And because we're working on open sets in Rn, to understand the Riemannian metric, we just have to know what does it do to a basis of vector fields, right? To understand an inner product, we just need to know what its values are on a basis of the vector space. So for example, we could just take our standard vector fields, but there might be some other choice of vector fields as well that we might find more useful. So the important point that I want to make here is that we have a natural choice of basis given by the coordinate vector fields, but that depends on our choice of chart. And once we do that, we can think of the Riemannian metric as a symmetric positive definite matrix of smooth functions, which is hopefully something much easier to understand. Okay, so now I want to move on to some very simple examples of Riemannian metrics. And the simplest one of all is just the Euclidean metric. So on Euclidean space, Rn, we have the standard Riemannian metric, which we denote by G sub 0, given by G0 acting on the basis given by the standard vector fields, partial I, partial j. If I want to know what G0 does to that pair, I just get delta ij. Now you might complain and say, why don't I say what G0, how it depends on the point in Rn that I've chosen? Well, it doesn't depend on it. That's what this says. It says that this Riemannian metric does not depend on the choice of point in Rn that I make, and so I leave it out. So this isn't G at the point 0, this is just G0 everywhere. And we call G0 the Euclidean metric for obvious reasons. Now I should have said, and I'll say it again later, that sometimes we'll drop the word Riemannian in front of metric when talking about Riemannian metrics on manifolds, just for brevity. Now what we see is that with respect to the basis given by the standard vector fields, this Riemannian metric G0 is nothing other than the identity matrix, right? The entries in the matrix are just delta ij, so it's just ones along the diagonal, 0 otherwise, which is unsurprising. So we see that we can identify, given this choice of basis, we can identify the Euclidean metric with the identity matrix. Now we also see is another way to think about this. I said it was an inner product, right? That's what the Riemannian metric is. It's always an inner product in every tangent space. So what is this inner product on Euclidean space in this case? Well, if we identify tangent vectors on Rn with just the usual vectors in Rn, then the Euclidean metric is just the dot product. That's not shocking, but it's very reassuring that it's something very familiar that we should hopefully all understand. So now I want to give the same example, but to illustrate an important point. So I want to think about the choice of coordinates, and now I want to think about polar coordinates. So let's define a map F from R plus times R to R2 minus the origin, given by, well, the polar coordinate map. F of R theta is R cos theta, comma R sine theta. Now we know that F is a local diffeomorphism, and so that means that we can push forward the standard vector fields on R plus and R. Let's call those partial R and partial theta. And then let's call those push forwards X and Y for simplicity. So then the push forward of the partial R, so let's remember, how do we do this? We look at the formula for F and we differentiate it with respect to R. And we get cos theta in the first direction, so partial 1, plus sine theta times partial 2. And if we want to compute the push forward of partial theta, we differentiate this with respect to theta. And we'll get minus R sine theta in the first direction, partial 1, plus R cos theta in the second direction, partial 2. Now, if we want to be clever, we can say, well, actually, what is cos theta? That's just the first coordinate x1 divided by r, plus the second coordinate x2 divided by r in the partial 2 direction. And we can do a similar trick here. And what we notice is that these two vector fields, well, they're the push forwards of a basis for the vector fields here. They're independent on r plus and r, so they're independent here, everywhere on R2 minus the origin. So to understand a Riemannian metric, for example, a Euclidean metric on R2 minus the origin, we just need to evaluate G0 on x and y. So let's do that. So G0 of xx, what's that going to be? is just the dot product of this vector with itself. So we're going to get x1 squared over r squared plus x2 squared over r squared, and that's, of course, 1. We can also see it here is just cos squared theta plus sine squared theta, which is 1. We can take the dot product of these two vectors, and we're going to get minus x1, x2 over r plus x1, x2 over r, so that's 0. These are orthogonal. And finally, we can compute what is g0 of y with y. Well, we see that's going to be x2 squared plus x1 squared, and that's just the same thing as r squared. So r squared sine squared theta plus r squared cos squared theta, r squared. So what we've seen is that the Euclidean metric with respect to this basis xy on R2 minus the origin is this matrix of smooth functions, 1, 0, 0, r squared. Now that might be a bit surprising because we saw that the matrix was a constant matrix before. For the Euclidean metric, it was just the identity matrix. Now it's no longer constant. It's some matrix of smooth functions. And we also noticed that this matrix stops being positive definite when r equals 0. But that's not a problem because we've assumed that r is positive strictly. And so this is okay. This is indeed a symmetric positive definite matrix of smooth functions, as we would hope. But we see, of course, a few key points that I want to make just to conclude this lecture. So some tips and warnings. First of all, the matrix of a Riemannian metric depends very strongly on the choice of basis, as we just saw. In the polar coordinates example, we saw that the matrix was no longer the identity matrix, it now was some non-trivial matrix of smooth functions. In particular, it depends on the choice of chart that you make, because then you'll get a different choice of coordinate vector fields. Notice also that we can always choose a local basis of vector fields so that the matrix of Riemannian metric is the identity matrix. We can always do that. But it's often not the case that that's the best choice of basis, because that's kind of a bit arbitrary. That's a bit too just algebraic. It doesn't see the geometry of the problem by doing that in general. For example, in the polar coordinates case, if we choose polar coordinates, then the natural vector fields are not the standard vector fields, but the ones given by the push forward of partial r and partial theta. Now suppose that you have a section of the second symmetric power of the cotangent bundle, so you just have some smooth choice of symmetric bilinear form on every tangent space, and you want to show it's positive definite. Then all you need to do is find some local bases for the vector fields on M so that the matrix that you get is positive definite. That will work. However, there's an important thing to notice. Just because you can find a matrix which is not positive definite, that doesn't mean that the Riemannian metric necessarily degenerates. You see, it's not here, it's enough to find a positive definite matrix to prove it's positive definite. But just because you found a matrix which isn't positive definite doesn't mean that this thing is not a Riemannian metric. That's what happened in what we saw in the polar coordinates. Remember that we had that matrix 1, 0, 0, r squared. That's not positive definite r equals 0, but it doesn't mean that G0 is not a Riemannian metric at r equals 0. It is. It's the Euclidean metric. It's well defined everywhere, but it's just a problem with the choice of coordinates that we made. So that's something to be very aware of, that you may have made a bad choice of coordinates. Okay, so in this lecture, we have seen the definition of Riemannian metric and Riemannian manifold. We've seen the basic example of the Euclidean metric, and we've seen how changing the basis can change the matrix of smooth functions that we find. And we've also seen that understanding this matrix is enough to understand a Riemannian metric locally. This concludes lecture 1